Starten. Okay, so we create a new project called variables. We will be just in the first lecture taking a look into the usage of variables and how they are represented in hardware. Zack. Okay, so okay, someone's asking that they download an app and whether they need a compiler. Well, the question would be which app did they download? So the person with the question in the chat can just unmute themselves and ask the question and provide some more information so that I can answer the question. Okay, well no one is speaking up, so yes, I hear you. Yes? Well, well, Visual Studio should contain a compiler. So if you install it and then run your project, then it should compile the application and execute it. Well, are you as far as in the currently shared screen, so you have a project and the main function where you can add some code? And then when you press just, for example, local Windows debugger, what does then happen on your system? Okay. Okay. So let's continue with the first project. So all the projects that I will create and show you during the lecture will be uploaded later to the Moodle. So you don't need to make copies or notes from whatever you see. This will be all provided. So on the hardware level, the computer can only operate with so-called basic data types. So these are formats for data which are represented in hardware and for which there are execution units which can perform these operations through a discrete circuitry. And the typical machine type which are available on most platforms are, of course, a single byte. In this case, we call it a char, like character. And in C, when you define a variable, you first specify the type, then you specify a name that you want the variable to have. The name can contain small letters, capital letters, underscore, and numbers, with the restriction that it cannot start with a number. And then optionally you can provide a initialization value, or you can not provide an initialization value. That's up to you and what you intend to use with the variable. And a character 1 byte is, as said, 1 byte, and it can hold values from -128 to 127. That the negative boundary is larger by 1 is a implementation artifact of how the binary representation works. So well, 0, but that we will take a look on later, so the internal binary representations. Now let's first write down all the other types that we usually have at our disposal. So the next one is short, which is 2 characters or 2 bytes. This one is already considerably bigger. 2, 3, 2, 6, 7, 6, 7. So as you see, the pattern that the negative boundary is always larger repeats. This will be for all the data types like this, at least for all the signed ones. Then we have int, which is the typical type that you would normally use in most of your code. So it's a number between minus 2 billion something 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 648 and so 4 bytes. And if you are lazy, we can just copy it and reduce this by 1, then it will get the right number. Okay, and now we're coming to the first data type. Oops, I forgot to name my int. To the first data type, which is not available on all platforms which are still somewhat in use with regard to computers, although it's on the way of phased out. It's the 64-bit integer. So all the old Intel-based systems, like before the year 2005-ish, supported only 32-bit integers and nothing larger. So if you wanted to calculate with a 64-bit number, you needed to basically break it up into 2 numbers. And then when the 64-bit architecture was introduced, you could finally use a 64-bit number which was supported by the hardware directly. And nowadays, with Windows 11, it's the first Windows operating system which no longer supports 32-bit hardware natively. So you can still, of course, run applications which have been compiled for 32-bit, but the operating system itself will natively only run on a 64-bit processor. And thus, for all modern applications, and if you are compiling to 64-bit, you can assume this one is present and has a very good performance. If you need to compile something to 32-bit, then if you use something bigger than int, then that will not be as fast in execution. But this is not really a limitation that is really a problem in the most use cases. So the execution speed with regard to integers usually is not really relevant. Now the way the variables can be defined in C is a bit it's not completely how to say it. You can define the same type of variable using different definitions. So instead of short, you can also write short int. Oops, I forgot the T. Instead of int, you can write long or long int. And for the 64-bit, since they already have used the long keyword before, they needed something else, so they decided that a good alias would be long, which is somewhat strange. But when you think about it, that the architecture was introduced initially with only 16-bit in the first Intel 8386 and or 8286 and like CPUs. There the initial architecture, which was used, for example, in the DOS operating system in the very old Windows 3.11, was just 16-bit based. So it was the default type which you had was the short, and then if you wanted to do something 32-bit, you needed long. So if you would compile something on a compiler for that platform, then if you would just use the int keyword, it would in fact default to be just 16 bits, aka 2 bytes long, and not 32 bits. And since you had your short, then you had your long for the 32 bits, so they then needed for the 64 bits something else, and they took long. Nowadays, if you are writing code for 8-bit microcontrollers like an Arduino, at least a large portion of the Arduino family, there are some 32-bit Arduinos available as well. But if you do that, for example, you must keep in mind that the default integer type on these platforms will be only 16-bit. So it's good to use data types as explicit as you can if you really want to have a portable code. Although in most cases, if you in most cases it would be difficult to write a code that would be fully portable, that uses all the features of the language, if you want to use it across the boundaries of a bitness of a system. One exception here is really the Intel or AMD 64-bit architecture, because the way the step towards the 64-bit was done is that the int remained 32-bit, and there was a new keyword like the _ int64 or long explicitly introduced for the longer data types, so that if you have a code that runs and compiles on a 32-bit system, you have a good chance that you can compile the same code for 64-bit and it will work without the need of any additional changes. Of course, if in special cases it might fail, but for the most part it works this way quite well. The next thing to know about variables and their representation is that they can either have the ability to display positive and negative values, or rather not display but rather represent positive and negative values, but they can also be used in a way, so the same 1, 2, 3 or 8 bytes can be used in a way that starts at 0 and then goes to for example, for the character case, to 255. So you can define which range of values you want to use. Like positive and negative values are useful if you are doing mathematical stuff, but if you want to calculate addresses or offsets in a file, for example, or other addressing related features, negative values are kind of meaningless. So what you want are values which are only positive, and this you can specify by using the unsigned keyword. So you can have an unsigned char. Oops, unsigned char, my own char, and this one starts at 0, not at minus anything. It just starts at 0, and then it goes to 255, and this doing this, it still only needs 1 byte of storage. It just changes the range which it represents. It does not change the amount of memory required, and you can do pretty much the same thing for all the other types as well. And in fact, there is also the signed keyword, so in principle you could prepend any of those with oops. But since by default all of those types are signed anyway, it is kind of pointless to do so. So let's quickly adapt here the ranges. So here we start, of course, at 0. Oops. 0 to 65,535. And the rest, so this has for 0 goes to 4 billion something 4,294,967 and 295. And one thing that probably you already noticed is that these are very odd numbers, so there does not seem to be, at least when you just look on it without any a priori knowledge, there is nothing that would look like why is this number, why is it not ending at some reasonable easy to remember value. The reason is because all the numbers are represented in binary, and there you only have a certain numbers that you can represent quite nicely. To make the representation of numbers in computers much more user-friendly, a representation that is often used is the so-called hexadecimal representation. So the numbers in this representation don't go from 0 to 9, but they go from 0 to f. And if we represent the numbers, the upper limits which we have here with those numbers, then for example the character just goes to 0FF, the short goes to 0FFFF, and so on. So as you... Yes? Hello? There was a question? No? No question? Okay. And of course here we have even more Fs. And for sake of completeness, what is recommended to add is you can if you want to initialize something with such a value, you can specify a UL or ULL to say that it's an unsigned long. In some cases this is helpful, and of course here when initializing we can also initialize the numbers with in hexadecimal notation. So as you see, 1 byte is represented by 2 characters in hexadecimal notation, and every quartet of bits in fact is called a nibble. So when we format this nicely, zack, zack. We notice that every hexadecimal value represents 1 nibble of this total number. What would next be important? So let's now see take a look on the binary representation of these numbers. So how these numbers are represented. One thing to say, which I showed but didn't mention, is if you want to write a number as a hexadecimal number, you have to prepend it with a 0x. This tells the compiler that it should use the hexadecimal representation. Of course, if you would have always letters in your numbers, then it kind of would appear to be obvious. But since of course you can have 0 or just 8 or any number you kind of want which is smaller than a, then this explicit specification is required. Otherwise the compiler would not know. If it just see, for example, 1/6, whether it is really 16 or whether it is whatever 1/6 in hexadecimal would be if you change that to decimal again. So 1/6 in hexadecimal, so 1/6 hexadecimal would be 22 in normal decimal representation. The old Windows calculator is quite nice since you can change between representations. And as you see, there is also the octal representation, which is quite peculiar. In this representation you can use only numbers 0 to 7, I think. Yeah, 0 to 7. And in fact the compiler is capable of processing these numbers as well, and if you want this representation you have to prepend the numbers with 0. So if you would write something like let's quickly write the examples down before we go to binary representation. If you would, let's say, write this is equals 12, then it's just, well, 12, that's clear. But if you write 012, then it will be in fact a different number. So you can test it again using the Windows calculator. If you go to the octal representation and enter 12 and then go back to decimal, you will see that it's actually just 10 and in hexadecimal it's just a. So this is an error that people might do because they want because in normal math, or normally when you are passing numbers, even if you are passing numbers from string, you would usually just ignore leading zeros. But in C or C++, a leading zero in fact is an indicator of which type the numbers actually are. So if we now take a look to our binary representation of numbers and write those down. So first let's start with the hexadecimal representation, then let's write down the binary, then in octal, and then in decimal. We will of course not go through every number, just for the most relevant. So null x 0 0, it's obviously 0. And in binary, if this is a simple character, it would be null x 0 0 0 0, and then null b and 8 zeros 1 2 3 4 5 6 7 8. Then octal 0 0, and in decimal it is just 0, and then let's be lazy and copy it. So 1 is of course 1, and octal is also 1 and 1. Okay, 2. Oops. Still 2. 4. So as you see with the binary representation, it just moves by 1 all the time, up and up and up. 8. And here we cannot use 8 anymore. So it's already kind of 1 0. Oops. In decimal it's of course still 8. Now 1 0. So this will be 16, and here it will be 2, and here it goes just 1 0 further up. We're almost through with all the, I mean, if we are lazy, we can just copy this part here. Where did we copy it? Here. Oh, we already have the first one, and then just shift everything by 4 bytes. 1 2 3 4 1 2 3 4 1 2 3 1 2. The deleted one too many. 0 1 2 3. Here I deleted not 1. And 0 1 2. Add this 8. 1 2 3. I forgot 1 0. I dropped a 0. Yeah, now it makes sense. Okay, so we just add the missing zeros to this, and here of course 20 30 100 200 16 32 64 and 128. Okay, so to quickly sum up the literals that we can use generally with numbers. So a literal is the representation of a number, how you write it down in your in your source code, such that it will be in a certain way interpreted by the compiler. Const int my var. That's so the decimal we already had. Then we have of course our binary representation bin. A binary representation starts with 0b instead of 0x, and then you can write, so if you want to have also 1 2 3, it would be 0 1 1 1 1 0 1 1. Then we can go int my var octal 0 1 7 3, and we also want the hex representation, and of course we need our terminating constant my var hex null x b 7b, and whether it's small b or capital B, it doesn't matter. You can use so the small or the capitalness yeah, of a letter doesn't matter in hexadecimal notation. So it's just for yourself whether you prefer small letters or large letters. And now let's take also a look on the representation of negative numbers. So as already said, with the simplest case of positive numbers, we have every multiplicative step of 2, it sets 1 byte. But if we want to take a look how this really works, so let's say this was binary representation in detail. Actually, I should just call it rather different representations, because we here also show octal and hexadecimal, so we just call it binary representation. So we start with positive numbers, but with a different range now. So of course 0 is null p 1 2 3 4 5 6 7 8 null, and in hex it's 0x0 0. 1 we also had, of course. 2 we also had, and the first new number which we learn is 3. And as you see, it just said, so in principle you can count binary on your fingers if you want, which is quite fun, although I'm not sure how useful it is. So let's go for 5 6, or maybe to not waste time I will just copy my cheat sheet with already filled out values. Then that saves us on some typing. Oops. So as you see, basically we are always flipping numbers. So we start with 0 to increase by 1 we flip. Then, and when we flip and we create a carryover, then it flips the next bit, and so, and the next bit and next bit, and so it moves until we counted to 16. And with negative numbers, it's as I already hinted earlier, it's kind of shifted by 1, because there is no like negative 0. The inverse of 0, i.e. all ones, or ff, is -1. And then for the next number, what you are doing is you are shifting in a 0 and then counting the zeros through. So it's kind of complementary to the positive numbers, just shifted in the representation by 1. And an interesting thing here also is that if you have a number which is unsigned, and you do operations with it, so like with this number, you can subtract. Basically, that works with all numbers. If you subtract too much, then you end up on the other end of the value range. So we can quickly test it. So if you would, for example, start with a number int my, so unsigned int my test is equals null x ff 7. Is it? Yep. Wait. Is this enough? Or is that one too much? This one too much. Okay. So that. Sorry, wrong. This one. If we run the code, then we can see what number we have. We forgot. Yeah. We copied something and forgot to change the variable names. When you copy code, it's a very common error to forget to rename something. So here, if we go to the locals page and then take a look into our my test variable, we have this 2 billion something something something. And now if we add to it, so this is equals +1, and run it again, we put a breakpoint here, then what you will notice is that the value, wait, sorry, it was unsigned int. Let's first start with signed integer and then go with unsigned. Okay, so again we have the value, and then when we add 1 to it, it jumps to a huge negative value, because what basically then happens is that the number now in hexadecimal representation, which we can enable, where was that? Here. So it then just moved 1 up, but then in the signed representation it's now a negative number, and it's in fact the biggest negative number you can have. If we do the same with unsigned, you will see that oops, my new test, you will see that the number here will just increase, so you will not run into this wraparound at this point. So you see it just changed, but then if we turn off hex, then while here it represents it as a very large negative number, here it's just still a positive number, just one bigger. You can however have the same sort of issue, which is called a value overrun, where you just have the computer behave not the way you might expect. So we insert the highest value that we can have in an unsigned integer, and when we then add 1 to it, then what it will effectively do is it will reset it to 0. Since it kind of adds 1, it wants to carry over 1 bit, but then there is no more room in the number for this operation. So the 1 that should be then on pretty much here gets just truncated, and you lose it. So it's important to keep track of the value ranges which your variables can hold. For example, if you have a loop or something that counts the amount of, I don't know, lines in a file or anything, you would not want to use a char because you would expect to have more lines than that. Often using a short might be enough for a loop variable, but it's usually of course recommended to just use ints everywhere, since it's just slightly bigger, but it avoids you errors if you don't if you might use much more end up using much higher values than what you expected initially. Using 64-bit is usually unnecessary, and another good thing to keep in mind is of course to whether using sign on unsigned numbers. A good example where you for example can run out of your value range in one of the smaller numbers is if you are doing something with files. Since a file can get larger than 4 GB, which is that much, then you would of course start having offsets which are 64-bit. So if you are using memory offsets or offsets in a file, it is always recommended to use 64-bit variables. So but that much to this variable overrun. Of course, another thing that you can let's say manufacture when you are using unsigned, well, signed and unsigned numbers, that works with both. If we start with 0 and then you want to subtract something from 0, but since it's an unsigned number, it cannot represent negative numbers. What will then happen is that your value will jump to a very high number, which also would of course in any reasonable case not be expected. So if you are subtracting something from some variable, it is always recommended to check if you actually can do the subtraction if you are using unsigned numbers. You can later look into some more practical use cases where this can become a problem. Okay, so one thing that also might be interesting is how to represent. So until now we only represented numbers, but the next thing which might be interested is how to represent some character. So if you use computers, you see that there is a lot of text in it, and even in the super old operating systems like DOS, you already had text, and in fact text is just represented, at least the basic Latin alphabet is represented using simple bytes. That's why the variable type is called also a character. And if you want to assign a character value to some variable, you can do it. Let's quickly go back to our literals. Const my char, no, my varchar, let's call it, and you do it by specifying the character you want to have in the single quotation marks. Now technically this is equivalent just to a number. So if you move your mouse over it, it will tell you that this is in fact just the number 1, 2, 3, and you can assign. So this assignment is pretty much equivalent as if you would just assign 1, 2, 3 or 3 no x7b. And this applies for all the letters that you have on your keyboard, at least assuming you have a normal standard non-Asian keyboard. The basic character set, which is representable by a character, is the ASCII char set, which in its basic form takes values from 0 to 127, although 0 and a few other values are reserved, so it starts somewhere around 20 where you have printable characters. But later it was extended to the Latin 1 alphabet, which then uses also values higher than 128, all the way up to 255 to represent like umlauts or other letters which are non-standard to the English alphabet but are used in many European countries. Another thing that I showed here but haven't mentioned is this const keyword. So let's explicitly mention this. You can define a variable to be const. So if you do it, then you can no longer change the variable in your code. So first let's make a non-const variable, int my var is 1, 2, 3, and this you can change at any later point. This will work just fine. But if you make it const, then the compiler will not longer let you assign a new value to the variable. And what in fact happens is that if you have a const variable which is defined as const, the compiler might, wherever it sees fit, replace the usage of the variable with really the value that you have assigned earlier. In one of the next lectures, when we take a look on pointers and casting, we will see how we can in fact change a const variable, but as said, since the compiler might take the value it expects there to be and use the value and not a reference to the variable, this is not something that should be done if you can avoid it. So it's risky in that sense. Let's here also just add as a comment that this is equals to our curly bracket. Okay, and obviously, as you probably expect from knowing anything about variables or any other programming language, and for what we also saw is our operators. So which operations can we perform with these variables, and those operations will be normally performed directly in the hardware of the CPU. So there will be a single instruction which can perform a given operation, and it is not implemented in like some well, at this level, hidden abstraction layer. Within the CPU there will be internal abstraction layers, but they are for all intents and purposes irrelevant to us. We usually also cannot even access those internal states, so we only care for the machine code representation of the code that we write. So obviously the one we already saw is value assignment. So you can just assign a value to a variable, either a literal like this thing is, or another variable. So we can, for example, create a variable and assign it, or let's create it without initializing it, and then assign it. And one thing that also is good to keep in mind with C and C++ is that all the variables that you define in your code always live within the scope of your code block. So all the variables we defined here only exist within the main functions code block or scope, and here if we add another scope, then the variable myvar2 will only live within this scope. After it we can no longer access it. So if you would have to here something like this, you see the compiler underlines it red because it sees that the variable does no longer exist. Normally these code blocks are associated with functions and ifs and other control flow structures, which we will take a look on a bit later. But for keeping your code more compartmentalized, you can use those code blocks also just everywhere you want. This works just fine. So then, of course, aside of the assignment operation, we have the typical numerical operations. Which I'm too lazy to type down. Since I already have a cheat sheet prepared, I will just copy it in. So it's addition, subtraction. Addition and subtraction we already saw with the value overflow examples earlier. Then of course we have multiplication and division, and then we also have the modulo operator, which is like it gives you the rest of a division. So if you divide two numbers in two real numbers, then you can always divide, and you will just get some fractional result if you if the number is not fully divisible by whatever you wanted to divide it by. With integers, what you basically do is you just discard the remain of the division. But sometimes you might be interested in the remain of the division and not in the actual rest of the division result. So therefore you have here this modulo operator, which you can use if this is what you need. And later, when we will do loops and pointers and stuff like that, I will show you why this operator is very, very useful indeed. One thing I forgot to say is, of course, one thing I mentioned is, since all these integers are just integers, just what's the the English word for it is, I think, integer. In German it's ganze Zahlen. But since you are scientists, you probably want to use floating point numbers, i.e. numbers which have a comma and then something, because you want to be precise in your calculations. You want to have as many comma places as possible. So, and since computers were created, of course, for scientific applications, they are also capable of operating with floating point numbers. The name floating point number refers to the fact that in the representation where the comma in your number is variable. You can in principle use representation with a fixed point. In fact, fixed point representation of non-integer numbers is used in the banking system worldwide a lot, because they like it. The difference between using a floating point representation and a representation with a fixed point is that if you have either an integer number or a number with a fixed point representation, that it's always exact. If you are using floating point numbers, the precision of your value will depend on the magnitude of your value. This is this results from how the value is internally represented, and if you are performing a lot of operations with these numbers, you may accumulate rounding errors, which in certain applications are of course undesirable. So in special cases it is necessary to use the integer numbers, and of course if you have an integer number, then turning an integer number into a fixed point number is pretty much just a question of how you interpret the number. You just say, okay, the last 4 digits are the thing after the comma, and that's it. So there is no special representation for fixed point numbers in the CPU architecture. It's just up to you to implement this in your program. But for floating point numbers, special hardware was required, and in very, very old CPUs, in fact, you had like a CPU that you put into your computer, and the computer then can already work, run some DOS application, and you had a second chip which contained the hardware for floating point operations. And an important thing to know at this point is, of course, that all the floating point operations you can in principle emulate using integer arithmetic. So you can, if you wouldn't have a floating point unit in your CPU, something which of course for modern desktop CPUs would be absolutely unthinkable, but something that on a very small system on a chip or a microcontroller like an Arduino might in fact be the case. The C or C++ compiler will abstract these away from you. So even if you have a hardware which does not support floating point numbers, you can still write your code with floating point numbers, and then the compiler will just implement a integer implementation, or rather use a library that does this already, and allow you to use all the floating point numbers you might ever want to use. So we have analogously to the integer numbers, so we have different sizes of numbers. We have here also different sizes of floating point numbers that a typical x86 CPU can execute. First one is float, that's short for floating point. And the literal for this is 0.0f, and it's a 32-bit number, so it's 4 bytes long, 32-bit, and it can represent this range of values. So it's, as you see, not super precise, and the highest number it can represent is limited. And in many cases you might, especially for scientific operations, you would not want to use a float. A float is good if you want, for example, for computer games. Floats are great because they give you the ability to already do all your full mathematical operations with all the things you want to expect. You get your 0.0 something results. You don't lose so much data if you do a division. It's everything nice, but it's unprecise. But for a computer game where you put something on a screen, whether it's 1 pixel off to the right, no one cares. If you do scientific application, what you would want is a double, or rather the full. It would be double float, but since people are lazy, they just allowed you to just call it double. Oops, double. The literal for double is very similar, it just does not have the F later on. And it's a 8-byte number, so it's 64-bit. And the interesting thing is that the floats with their 64-bit internal representation were available already in 32-bit CPUs. So it's not like you needed the AMD X64 architecture to get 64-bit. For mathematical applications, you had this even in old Intel chips already available. And in fact, nowadays there is in some applications the trend to go actually to even to lower precision than a float. To this in a second. But to finish up the double story, as you see here, we have a much larger value range which you can represent. So as you see, with only something to the power of plus or minus 38, that is for many scientific applications really useless. But if you have something to the power of 308, that's a different story. That's pretty much good enough for most applications. Now, as I said, in certain very special edge cases, there is this there is almost no need for precision, and in fact this is used around artificial intelligence or neural networks in general, because there you want something to just do roughly something, and then you have a huge amount of these somethings cascaded one after the other. So you don't need precision, and you don't even need the calculation to actually be correct. So first of all, what you get with all these AI accelerator hardware types of hardware is that you have data types which are floating point but only 8-bit, or at least only 16-bit, so that you can use even less precision. And another interesting thing is that those chips are often run under conditions which would allow them to do allow them to make mistakes. So if of course, if you are training a neural network, you might not want it to make any mistakes. But if you are really just executing it for some speech recognition, if you can save half the electricity by allowing a 1 in 1,000 error, which by the nature of the network will not really influence your result, then it's fine. So with AI accelerators, it is common to run some of the implementation, at least at voltages which will give you the best performance per voltage without guaranteeing the result being exact. But since the whole AI stuff and neural networks are not really an exact science, people usually don't care. And this is also why our brain is in fact so energy efficient, because it's not very exact. If you want to take a look into for yourself to the limits of all these different data types, I pasted in here a link where you can review all the value ranges for the different data types. Now, another thing about data types that is good to know is that modern CPUs in fact support more data types than these basic types that we have yet taken a look at. Those other data types are usually something that for most applications, when you're just writing your own program, you will not care about. These are usually a vector data type. So basically, like, you can have 4 integers one after the other, and then if you have a variable of this type and then just copy the variable, then it would give you a better performance when doing the copy operation. Or if you want to add or subtract 4 integers from another 4 integers in one operation. It is when you implement operations in hardware, it is favorable to implement many operations of the same type instead of allowing every operations to be different. So these vector extensions, which you can find in modern CPUs, they are labeled as MMX, later SSE, then SSE2 and SSE4. Now they are labeled AVX, and this goes up to AVX 512-bit. So in fact, you can have a vector of quite many integers, or this also works with floating point numbers, and then do one operation on the whole vector of numbers. And this in fact is used in computer games or video compression, also in scientific software packages, to greatly improve the performance of the software. It works much better than if you would really like make a loop and then make one by one in operation after the other. This is good to know, but this is not something that when you are writing your own applications you would usually resort to using. In special cases, yes, but in generally it's something that you don't need to take care of yourself. So, but coming back to these operators here, let's make an example. Oops. Let's make an example of it. So let's make a variable int var1 is like 1, var2 is 2. We are of course starting with very basics, but it will get complicated quite soon, so don't worry. It will be interesting shortly. Let's say a multiplication var2. And now we can put a breakpoint here and run the code, and then see in the debugger what the compiler made out of it. So if we have just normal 64-bit code, then look on the compiled representation. So of course we have our assignment operator. So here the compiler uses the move instruction, which takes a address and the value to move something to, and then it copies basically the number 1 into this memory location. Then it does the same for the number 2, and then here we have our execution of the operation. So you see here it then kind of does the opposite. It loads a value from memory into but this time into a register. It doesn't use a fixed value, but it loads it into the EX register. We can down here take a look on all the registers which are available. I will talk about those registers shortly, but first just see that the AX okay, maybe I need to talk about them right now. The way the registers are named, AX is an artifact from the 32-bit era, and if you use the name AX, it will just use a 32-bit number, but it will still put the value into the error AX register. If you use the error AX name for the register, then it would be to a 64-bit operation. If you do it with a 32-bit operation, it will just blank out the top bits. So if we step through the code, as you see, it loaded the value 1, and now what we can do, what it does is it invokes the opcode for multiplication, and it tells it take the value of the AX register and multiply it with whatever is in the memory at this location, and the result of the operation will be written again into the AX register. So now at this point we are done already. So if we step one more step, we are done with the multiplication. Our AX register now contains the result of the operation. Admittedly, with just 1 and 2 it's a pretty boring example. But now we need still to write down the result into the memory of variable 3. So this is here this operation. Again, a move instruction, but this time it doesn't take a literal, but it takes a register name, and then it will write to the given address the integer, the 32-bit integer. So in fact we can, if we put this into here, we get the exact memory address. We can then go to memory. Should be somewhere here, and now if we make a step we should see the memory change. Yep, and we see here the memory changed as expected. The new value was written into it. At this point it's good to note again that, as I said the last time, the compiler, when in debug mode, in which we are right now, creates a code which is very exactly representing the C or C++ code which we have written. If we would compile something for a release build, the compiler would actually just throw away all of this because it's inconsequential. But if you would have some real code that then does something, then what it could do is, for example, here it would just assign 1 to register AX directly. Here it would assign it to another register like ACX, and then it would just do the operation with the registers and write only the result out. Another thing that is interesting to see is what happens if you want to go 64-bit. So now we just change everything to 64-bit and rerun our code. You will see that the code looks pretty much exactly the same. It loads the two values, then it makes the operation. So it saves the two values into memory. It loads the value, it executes the multiplication, and then it saves down, just that it uses the RAX name for the register. So the code that you see here is the assembler representation. So if we would go to this address in memory, you of course just see something that is unintelligible to people that usually are not used to read machine code, which pretty much no one is. Everyone that works on reverse engineering or understanding what some other application does is doing it in a disassembled view, and there is a nice tool that we can in fact use for that. So of course you have a disassembler in Visual Studio, but if you just want to disassemble some things on your own, there are these websites like this one, or that one, where you can paste machine code, and it will produce you the disassembly output, which is often quite useful. So in this example here, we can grab the code. Oops, the code to here. Then the code. Then we go to our disassembler. We tell it it's 64-bit code. We paste the we need to clean it up slightly because it pasted also the other representations. We only want to paste the hexadecimal representation into this. Suck. And it will also disassemble. Now here it's a bit more because we just grabbed the whole function, but you also see we have the move operation, we have the other move operation, so we assign 1 and 2 to two variables, and we have here we load something into regex and again multiply and then move the result back out. So this is quite useful. The links will be in the project for later reference. But now let's do something in other, and namely switch to a 32-bit build. So let's see what the compiler does from our 64-bit variable usage if we tell it that it should compile it for a 32-bit CPU. And although it needs a second to load all the symbols. The compiler sometimes is quite smart about doing it, sometimes not, depends on which operation you do. But for example here you already see that it needs much more operations to do the same thing. So just already the assignment is quite a large operation. So first, so XOR is a logical operation, and it is used often to clear memory, because if you XOR like 1 and 1, then the result is 0, and if you XOR 0 with 0, the result is also 0. So if you XOR something with itself, it will always result in 0. And the representation of XOR and two registers is very short. So if we, for example, take this code and paste it, I closed it already, into our online assembler. So the assembler can also assemble it, it can do both things, but now we want to be 32-bit. Then it only needs 2 bytes for this operation. If you would want to do something else, like assign a number, then we would need already more bytes usually. So this is why the compiler does it this way. And then what it does is, at the lower portion of our memory it writes the 1, and in the higher portion of the memory it writes our register which contains 0, and then it repeats the same trick for the value 2. And then when we want to do the multiplication, it needs again 4 operations, and then it will in fact call a function which will do the multiplication, and then it needs again 2 operations to save the result. So this is what I mentioned earlier, that it's good to just always use normal 32-bit integers unless you need 64-bit, because then on every platform you will have a very efficient code. And one thing we can try out maybe as well is how this code would look on a different architecture. So if we switch back quickly to the 64-bit case, and then we can copy the code that this resulted in. So we only care for this portion. Zack. Let's quickly write this down in a multiline command. So that's x64, and then we can, for example, take a look how this code, the same code, would look on a ARM platform. So ARM is a well-known RISC architecture. RISC stands for Reduced Instruction Set, while CISC stands for Complex Instruction Set. And mainly, well, the main obvious difference between those two instruction sets from like an ideological standpoint is that in the complex instruction set you can have instructions with do something with registers and with memory, while in a reduced instruction set the only operations which can do something with a memory location are operations which load values from memory to registers or from registers to memory. The result of this is that pretty much, except those very few opcodes, the whole rest of your opcodes always operates on registers only, which allows for a somewhat more efficient implementation. So now let's go to our project settings and add some ARM platforms. So we go to the configuration manager, new one, ARM. Let's go with but that will be 32-bit ARM. Okay, that is not great. I need to add this component, I think, to Visual Studio. I might forgot to do it before. It should not take long, since it's just one small compiler toolbox which we're missing, and then einzelne Komponenten. Okay, so we need this and this build tools, and here this. Nope. That should be everything. This one, we don't need also the mitigations. This one as well. Okay. Okay, that I hope that will not take too long. Are there any questions at this point? Okay, if there are no questions, then well, try writing long instead. Well, it depends on the compiler. So, which one are you using? Are you using Xcode from Apple, or are you using GCC? Okay. I think underscore int64 should work on GCC. Yeah, underscore int64 for GCC as preprocessor option. That should be right. You need to add the. Okay. Do they really not? Okay, they might not have it, but you can use a type def to define yourself a placeholder for that. It might be that the underscore int64 is a Microsoft own thingy that they equivalent in GCC. Yeah. Well, you can use i64 underscore t instead. That should work on every platform. But I might assume that Microsoft did not added this on their compiler instead. Yes. Yeah, the long is probably the most reliable option, because the something underscore t is usually used by GCC and I think Clang as well, but I'm not sure if in the standard headers for Visual Studio you have the int underscore t types defined. I think you need to define them manually on your own. Okay, any other questions? Okay, so since, as I said the last time, we are usually expected to have a 15-minute break somewhere during the lecture, I think the installation of this package is a good time to make the break. So maybe not 15 minutes, but let's say that we make a 5-minute break and resume at 16:15. So in 5 minutes from now. If you have any questions, I'll be here on all the time, so you can ask away. Yes? Well, size t is a placeholder type, so it's not like a machine type. Size t as such is not a type that describes a type that the CPU processes. Size t is a placeholder which the compiler then will replace with either int or underscore underscore int64, or in fact a short if you are doing something on Arduino, and it will always be the integer type which is the largest one supported by the architecture for addressing. So I would not say that you should use size t for loops, because I don't expect loops to go past a few 100 million operations. But you should use always size t if you are referring to sizes of memory blocks, or if you are using it to address a memory offset somewhere, because using size t will guarantee that you will not run in a scenario where you would want to have a larger memory block than what your type can hold. So if you would, for example, use a short or an integer for your memory block size information, and you would allocate a 5 GB large memory block, then in fact the result in your value would be just 1 GB, which would be completely wrong, because it would cut off the higher value. But using size t guarantees that it will always be the right type, and it's also helpful when you are doing any sort of offset arithmetics, that you just always use the same type. Then you know that in no scenario some data loss may occur. Any more questions? Okay, since there are no more questions, maybe I can say something tangential to this size t question. If you are you can use other placeholder types as well. For example, there is the int underscore ptr, which in principle will give you an integer type for for the maximum pointer size supported on a given architecture, or you can use a uint ptr if you want an unsigned version of that. And there are in fact quite many pointer placeholder type. So as we already saw earlier with the quick search for the 64-bit integer for GCC, it is customary on the Linux like platforms to have data types like int 8 underscore t, int 16 underscore t, int 32, and int 64 underscore t, which all then represent just the different types, and it's more descriptive than using int, short, long, because it's in the name you have already the amounts of bits that the number will then hold. So this in this sense is more user friendly. Okay, we have 1 more minute to wait, since we said we resume at 15 after, in case someone went for a short break. But we can open this and check actually whether that works. It's already 15, so we can continue with the lecture. Although I said it's a bit a too short break, we should make longer break. So again, we go here, we want to add a new architecture. Now we can select ARM64. You might notice there is also a thing like ARM64 EC that is something for to enable a certain level of interoperability. If you have if you want to run Intel architecture code on a ARM Windows, you can do it through emulation, and you can create libraries which are of the ARM64 EC type, such that they can be used by Intel code, but which internally are ARM code. But that's just a small tangent on the side. So here for our example, we just select the 64-bit ARM. We want to copy from the 64-bit Windows example. Okay, and now we can select here ARM. One thing, of course, that is obvious, that we will not be able to directly run the code here on the virtual machine, since it's a Intel virtual machine, so it is not ARM compatible. But what we can do is we can run a Windows on a Raspberry Pi, and then we can use a remote debugger. So we have our Windows, we have Raspberry Pi, we want ARM64 Visual Studio 2017, so we start our remote debugger. Then we can start some process we will want to debug. Then we will want to copy the file that we have created onto our target platform. Media temp. Okay, we don't have access to temp. Oh, we might not have access anywhere. Then we need to make access Schaften. Okay, zack, temp. Okay, it forgot our variable. Slightly too slow. Let's just copy it again. Zack. Okay, stupid Windows. Did we just crash our Raspberry Pi? Yes, we crashed the Raspberry Pi, and there is some issue with the Windows for Raspberry Pi that it sometimes crashes when you access it through Samba, which is annoying. It's yes. Yes, yes, it will be uploaded to Moodle after the lecture. Okay, great. The Raspberry Pi is quite a nice platform, but it's not quite well suited for running Windows. As you saw, we just crashed it just by accessing it through Samba. I'm not sure why this is happening, but sometimes it happens. And it's quite slow, so it's still rebooting. That will take a moment. Okay, it rebooted, so we start our debugger again. We will need to reopen the Explorer since it did not remember our newly shared temp folder. Freigabe again, Freigabe. Strange thing is it mostly only crashes when you try to list folders. If you would copy things through the console, it would be fine. So here we copied our variable. So let's close this. Let's again open a test application like this. Wait, that should work. Debug. Attach to process. Again. So debugger attached to process. So this is the process if you want to debug something on a different platform. You can specify the address. Do we need the port? 4062. 4062. 4062. Okay, it complains. 4062. Is the network not set up properly for that example? Bridge network should work fine. Well, it should be able to connect. Default should be fine. And that should work. Why is that not connecting? that usually worked. I tested it recently, that worked just fine. Let's try it again. I will reboot that as admin, and then here I will use the IP address directly. Maybe it's something with the naming. .40. Damn it. It's 26, not 62. Stupid mistake. Okay, so we attach to this. Okay, I forgot one more useful thing. I will need to make this somehow. Wait. We need a small update. We are missing a plugin, so I will do it differently. There is a nice plugin that allows you to connect to child processes of processes which you are already debugging, but I did not install this one. So I'll just add this get char here that will make wait the process at the beginning. So variables will just damn it, it needs needs a certain slightly improvement. We need some additional files for it to work. That should work. Okay, now it's waiting the bug. Attach to process, variables, attach. Okay, we have our breakpoint here. So now we just press enter to make it continue to the breakpoint, and now here we are in the ARM code. So as you see, it looks on the first glance it looks completely different because it uses different names for the operations, but the LDR just stands for load register, and STR stands for store register, and while on ARM you have different names, on x86 you just use move for everything. So we can quickly copy the code here for our own purposes, and as you see, with these very simple programs, the only difference really is that instead of being able to do the multiplication directly using a memory address, it needs one more register. So in this case it uses the registers x9 and x8. It fills them with the two values which before that it has written. You also notice here before in the 64-bit case we only had one instruction to save a literal to a memory address. Here in fact we need two instructions. So maybe we should actually copy the whole code into our sample, since that's also not so bad, and then we can go back to our normal 64-bit code. Okay, so again if we are here, now it's waiting for the enter. As you see, again it's just one line, so let's copy this here. Zack. And one thing that is quite obvious, of course, is that in this reduced instruction set or on ARM, you really often need a larger number of instructions to do the same thing than what you need on x86. The theoretical advantage is that since the instructions are simpler, the idea, at least back then, was that you can execute more of the simple instructions per unit time. So you can have kind of faster CPUs, and of course if your code is highly optimized, it can take advantage of it. Nowadays, so So like in the good old days, maybe I should start this way, a lot of instructions needed quite a few more than just one clock cycle. So for example, of course, a multiplication or division would take forever, like in dozens and dozens of cycles. But even simple instructions like load something to a register or add two numbers, and if you were using memory addresses in your complex operations, then it would need a few clock cycles, because internally it would dissect the operation into a few micro operations, which then would be executed one after one during each clock cycle, and effectively this would this seemed back then not to be that efficient. Nowadays the CPUs are using so back then, maybe I should say this way, back then you had a lot of time, but what you didn't have was a lot of transistors in your CPUs. So you tried to do things to break down things into multiple steps, even if this makes everything slower, but it at least makes it possible for you to manufacture the CPU. Nowadays you can have billions of transistors on a CPU, so you can implement many things in parallel, like operating in one go, so that you are not wasting CPU cycles executing that discrete steps of an operation, but really can do a much more complex operation in one go. So many instructions which on the old CPUs took long, on modern even complex CPUs will be executed very fast. And another thing to note about this implementation artifacts of the modern CPUs are that for some of these instructions they still will be dissected into multiple internal sub-instructions, but since this is done for every instruction that comes into the execution pipeline, and often the instructions not necessarily depend on each other. So for example, this instruction and this instruction, they do not depend on the results of each other. They are completely independent. Only the next and even this instruction depends on this one, and of course then this on everything that comes before. But the way the CPUs work is they dissect your incoming complex instruction into a couple of micro operations, and then they kind of are able to execute many of those micro operations in parallel. This is called out of order execution, as long as the results of these operations don't depend on each other. Of course, there are limitations. So if you have data dependencies, or if you have branching in your code, so the CPU doesn't know which instruction will be next, then the pipeline is halted, and it first has to complete the execution. But in many cases you will see that modern highly optimized complex instruction set CPUs are just as fast as ARM CPUs. The only thing where ARM CPUs are really, as it looks, hard to beat nowadays by the old Intel architecture based CPUs is efficiency in terms of instruction per watt, because the complex CPUs have to decode all the instructions. They have a lot more overhead, and while they can kind of gain speed by throwing more and more silicon on the problem and parallelizing more things, or even doing like speculative execution, so they assume, okay, probably the next instruction will be this one, because like if there's a branching, the branch either will be taken or it will not be taken, and it will try to predict what probably will happen next, so it will preemptively start already executing the next instruction. And when then it really has the result which is relevant, then it will see, okay, was I right with my guess or not? And if the CPU was wrong with the guess, then it will just discard this half-done results it already pre-computed for the wrong branch, and then it will have to redo the operations in the right branch of the execution flow. But well, there are many reasons why this is a bit problematic. So one was that this execution of code, which in the end does not really gets executed, can still leave detectable traces in the CPU. So there were a few of these security exploits found a couple of years ago, called Meltdown and Spectre, where you can bypass security checks with regard to memory access in the CPU for this speculative execution, and you can set up everything such that the speculative execution will, for example, change the timing at which you can load something from the CPU's cache. So then if you have code which then actually gets executed, it could, by measuring timings, infer on some execution artifacts of code which was executed and had access to data to which it shouldn't have any access. So this way you can exfiltrate data from memory regions which you should not be able to access. So there's one issue with the speculative execution, that it's prone to leave leave opportunity to find security exploits. But the other issue, of course, is that the more it speculates on execution which then will be discarded and not used, the more you are wasting CPU cycles and energy. So the ARM CPUs, which nowadays also do to some extent speculative execution, they do by far not need to do it to that high of an extent. And also if they have to discard some of the results, it's less, because you have more individual operations. So it's likely that you will have to throw away less of your data if your speculation was wrong. And another thing that is interesting to know about these differences here is that if you really don't care for the efficiency but really want the highest performance you can get, you can in fact have better performance with this CISC based systems in many usage scenarios. Simply because you have a much higher code density. So on the ARM platform, every single instruction, no matter what it does, will always be 32-bit long. And if you have, for example, if you have a lot of constant variables in your code, you will need to put them somewhere in your code and then jump around it. You cannot write very large 32-bit numbers into one opcode. So in the CISC case, in this move, we only used one, but we could have had here 0xFFF inside, and it would be just fine. On ARM, you can usually go up to a short at most. And if you have a bigger number which you want to write to a register, then you need to have the number somewhere, then you need to reference the other address. So it gets complicated very quickly, and it very quickly escalates to having more and more and more instructions to do something. And then you need, of course, a very high memory bandwidth to keep the execution units of your RISC CPU busy. While in a CISC system, you can you don't need this much memory bandwidth, and you really see that, for example, on multi-threaded tests, when you compare a Raspberry Pi to some other types of CPUs, you really notice that even if you get a very good result in a single-threaded benchmark, as soon as it becomes multi-threaded, because it's a small SoC and it doesn't have many memory channels, it only has one in fact, you will see that the performance tanks quite significantly. Okay, but that much to this small detour on the different architectures. Of course, you can use any of the operations here. That's obviously obvious. The next interesting thing probably we should mention is which registers can you use in the assembly code. Now, for writing the C code itself, it is not so important to know the registers, but if you ever do something low level or want to check something in the assembler, it's nice to see and to know which registers are available. So there is a short list which I'm too lazy to type down. So let's x86/x64 stars. So one register is of course the instruction pointer that tells you where you are in your code execution. So when we again run our example and end up in the debugger, then where the debugger shows that we are within the thread, this address will be in this register. And when we then progress to the next execution, okay, it will change the register again. So we have a register which always keeps the memory address of the currently being executed instruction, and or rather, technically it's the next instruction to be executed. So you could change the register, and then the thing would go somewhere else where it shouldn't go. And there are quite a few instructions that do this, in fact. So this is the instruction pointer, and in the 64-bit version of the Intel x86 architecture, you have the same registers as you would have normally. So like in the 32-bit, everything starts with an E, and in 64-bit, all of the registers starts with an R. And then you have an additional set of 8 more registers, R8 through R15, which you can use in your code. And if you look on the ARM architecture, you see here we use the register X8, and on ARM 64 X0 X31, and the instruction pointer is one of them, and a couple other registers which have special purposes. So as the name says, the idea behind ARM is to keep everything simple, so they also didn't bother naming the registers, at least most of them, in a particular way. They just count them through 0 through something. Yes, that much to the registers. We will later take a closer look on how those operate when we take a look on function calling and control flow, etc. One thing that is, for example, to be taken into account is that when you are calling a function, that the function may also use registers, and in fact the definition, the API definition tells you that some of the registers are volatile, so if you call a function, you can expect them to be changed, and so basically you can use them, and after you call the function, you have to refill them with whichever values you want. And there are other registers which are defined as non-volatile, so if a function wants to change those registers, it has first to save the old value, and then before it exits, it has to restore the value that it initially had in those registers, such that the calling function can rely on, from its point of view, the value of those registers staying the same. But as said, this is something for later. And one more thing to say about these registers and their naming convention is that the naming convention in fact goes back down to the era of 8-bit CPUs. So like the 16-bit, that was DOS and so on, and but before that Intel also had a very early 8-bit CPU, I think Intel 8088 or something like that was the name, which really operated just on 8-bit words, and there you only had 2 registers, AH and AL, and the way the naming later evolved is that if you have your whole 64-bit register, you have your upper portion, which is only available in 64-bit, and then you have the lower portion, which is represented by AX, and then this AX, again, you could use EAX, and then you could also use AX to access just the lower 16-bit of that, and then you could also use AH and AL to access the individual bytes within your 32 or 64-bit word. So this is something to take into account, and also when you watch code in the disassembly, you can see with which number, with which type the code is operating. So as already mentioned earlier, if the numbers are 64-bit, it would be RICE. If they would be 32-bit, it would be EAX or any of the other ones. In fact, those registers, additional registers here, can also be addressed in a 32-bit mode. In this case, you would use D8 through D15 instead of R. And I think, to my knowledge, there is no addressing for 16-bit for those registers at all. For those higher registers which you have available in the 64-bit mode. Okay, this much to the registers. Let's continue with the different operations that can be done. So of course, as said here, we have the typical mathematical operations, but then we also have comparison operations. So where you are comparing different values with each other. So if you want to compare two variables or a variable and a literal, you could of course also compare two literals, but that would be pretty pointless since the result will never change. You just use a double quotation mark. So the single quotation sign is only used for assignment. It is not used for comparison. In some programming languages this might be different, but in C it is important to note that if you want to compare something, you need the double comparison, the double equal sign. And in fact, for beginners, it is a common mistake to write your code, and when you want to compare something, just press equals once, and then instead of comparing a variable, you will overwrite a variable, and then of course they will be equal. So it is a common source of mistakes. The compiler tries to catch this. So if we would on purpose write an example that does this, let's do that. So int var1 is equals 1 and var2 is equals 20 if var1 is equals var2. So this is the bad case. I really hope it will warn us. It will compile, but it should produce a warning. It did not. Then we need to crank up the warning level. It's a code generation. Active, yes. Warning, where was that? General probably. Oh, we can go to all option and then look for. Okay, so we are at warning level 3. Enable all warnings. Let's just go all out with that. And let's remove this get char because we don't want it to wait at the beginning for an enter key, and we don't need this breakpoint either. Okay, so if we now compile it, it should. Okay, that were quite too many warnings, because it was also complaining about we are not using variables and stuff like that. But here, warning C4706, assignment with conditional expression. So they don't want you to do it, and you should not want to do it either. What you could do if you really want to assign, and because this functionally is assign variable 2 to variable 1 and check if variable 1 is not 0. So this is functionally equivalent to this. And if we have this, then it will not complain, because it sees how we know what we are doing. It's intentional. Of course, we have all the other unused variable warnings, so I will turn this back to level 3, since we don't want to be annoyed too much by too many warnings. But I said the right way of doing it would be just to have var1 is equals var2. And since we are not yet having a control flow, we should have int var3. We should do something like this. Control flow will be a later part of the lecture. Oops. And of course you can use, if you want to see if they are not equals, the exclamation sign equal, and you can of course make greater or greater equal, and here really greater is greater than, and greater, or rather, yeah, and greater, wait, greater than. This is not consistent. So left is smaller, that should be less than. And this one we move here for consistency. 2. So in this case, as I said, you don't have this additional equal sign, and here you, as in math, you don't have like a ASCII character for greater or lesser or equal, so you are just instead using 2 characters to kind of make it look like what you want. Here let's go with the equals. We can also take a look in the machine code how this would look. Obviously the first 2 lines we already remember. It just loads 2 things into memory. Well, it in fact here is does it in a quite convoluted way. So it loads one variable into the AX register, and here it compares this register with the other variable, and then it checks. So it makes a conditional jump. It checks if not equal. So if it wasn't equal, then it will wait. Then it will jump over this code to h to here, where it will write 0 into this memory region. Or if it's equal, then it will go past this operation to this, assign 1. This is wasteful. And then jump over this instruction to get to this this line, yes, where it will write the result in the AX register just to later write the result into the other memory location. So at this point, of course, it's still quite inefficient all that it's doing here. If we would compile this as a release build, it would be more efficient, of course. But for now, I said we want to see how this code looks. And the next set of operators which we can have are logical operators, which in turn so first we have logical operators as we can use in conditional expressions. So we have a logical AND, a logical OR, and a logical NOT. NOT is just a negation. So the simplest case, of course, is we can have this, or A and B. Functionally, that would be equivalent to that. Wait, not quite. So if this is so if these variables are not the same, then the variable 3 will be 1, else it will be 0. And here it does the same thing, just that it uses the other comparison and then negates the result of the operation. And we can of course use the other logical operations to make more complicated things. So let's add some more variables. Let's say this is 3 and 4. 3 and 4. I don't know. Let's keep it at 1 and at 1. And then int var5 is equals, for example, var1 is equals var2, or we negate var3 is equals var4, and this, as already mentioned, would be equivalent to that. So there are sometimes multiple ways how you can write the same thing. Yeah. And so the OR means that if this is true, so if this evaluates to 1, then variable 5 will be set to 1, and that's it. If this does not evaluate to 1 but evaluates to 0, so if it's false, then it will check the rest of the expression. And here, if this thing evaluates to 1, then it will set it to 1, else it will set it again to 0. And the important thing to remember about this is that when it will construct this condition, as we saw here, it will not do it mathematically like by adding the results, but it will do it programmatically. So it will do a control flow. So if this portion of the code will be true, it will then already not execute this portion of the code. We can in fact try this out. If we make a condition that is true, put a breakpoint here, and then take a look how this will behave when we step through it in the debugger. So we start by loading. What did I pass? Yeah. If you are in the if you are focused on the source code and not on the debug output, then the one step just steps the whole line. We don't want it, so we need to click here. So here we load our variables. We make the comparison, and then this JApp brings us already there where we set it to 1. We skip this whole code block in the mid. This whole code block in the middle, because it was already satisfied. When you only work with variables, that might appear it's inconsequential, but as we will see later, it is very much consequential, and also might be a source of errors. Okay, so that much to those operations. Now the next quite interesting thing is the so-called trinary operator. It is called trinary because it takes 3 operands instead of 1, and it can be used already for a sort of control flow. So int var1 is equals 100. We again need some test case for that. Let's go with let's call it var, and then let's call it var 1 0, and then we make int test is equals, and then we make some condition var1 is greater than var2. Okay, and now we use the trinary operator. So first operand is a condition. The second operand is a value or an equation or anything. So we could, for example, use var1 plus 1. Then we use the double point, and so basically everything between the question mark and the double point can be considered to be in brackets. You don't need to do it because it knows the order of execution. And then the next thing, which is after it, which is good to put in brackets because you might have some here or surplus so that you know how far it goes. But since we have a very simple case, we don't need the brackets. var2 plus 2, let's say. And what this means is, if this is true, then assign var1 plus 1 to test, or if this is false, then assign var2 plus 2 to variable test. So kind of, if you would want to write it as an if, then it would be if this, then test is equals 1, and else test is equals 2 plus 2. Control flow will be in the next lecture, I guess, unless we are fast enough this time to get to it. So there we will take a look on this ifs and other things. But the nice thing about this operator is that you can use it to inline some decision making. So if you are, for example, calling a function and have two different variables which, depending on some other condition, one of which you would want to pass as one of the arguments of the function, then you can use this trinary operator there instead. This is quite nice. And now we can take a look on some other operators, namely the incrementation and decrementation operators, plus and minus, and what they do, in a way, they are just stand-ins for other operations. So if we have int var1 is equals 1, then we can write int test 1 is like var1 plus yep. And this will result in var1 being 2 and test 1 being 1. So this sort of expression, it takes the old value, copies it to your result value, and then increments it by 1. So it's pretty much equivalent to test1 is 1 and test1 is equals test1 plus 1. It's kind of the same thing, just that it's much shorter to write down, and it works the exact same way with minus. And there is a second way how you can use it. Int var2 is equals 1, int test2 is equals plus test2, and now it's different because now var1 will be 2. Wait, yes, and also test2 will be 2. So this evaluates to a very small change in order of operation. It first does the incrementation, the plus 1, and then it does the assignment to your result variable. This is especially useful in loops or in other conditional expressions. And when you think about that this operator is changing the value of our variable, you notice that if we would use it, for example, here as a part of the second condition, it would not always do the incrementation. So we might run through the line. We can write such an example down, or rather we just copy this example. So if we copy the example, then we make another test. So let's say or var2 is is lower than 10. And just to be on the safe side, we put this in brackets so that the compiler definitely takes the right order of operations for us. And here, warning var will not always be executed. And of course, if you have functions in your equation, so a function can return a value, so you can use the result of a function in some equation. If you have a function as a part of such a logical expression, for example here, and the first case already triggers, then the function will not be executed at all. So this is something which might not be intuitive to all people. Because on one way you might think, okay, if you have function calls, then we'll always evaluate everything, write everything down into temporary variables, and then do the math. But quite differently, it really does the math as long as it goes with the control flow, and then some of the functions might not end up being executed. The next thing which we can here take a look into are some so-called combined assignment operators. So here what you can do is you can combine one of the mathematical operators we saw earlier with an equal sign to also again save on lines of code. So for example int this var1 is equals 1, oops, int var1 is equals 1, int var2 is equals, okay, let's say, yeah, var2 is equal, it doesn't matter, var2 is equals no, that's a boring case. Let's just go with var1, and one way to do it, for example, would be var1 is equals var1 plus 1, like I wrote, for example, here for var2. But what you also can do is you can write alternatively var1 is plus equals 1, and this is semantically equivalent. var1 is equals var1 plus 1, just that you save on typing, you don't need to retype the name of your variable, and this works with those operators, and it also works with other operators as well. So this saves on programming, and of course the advantage is that you can then use 2 or any other number. With the incrementation and decrementation operators, you were limited to only +1 or -1, while here you can increment it by any step you might need, and it's still quite saving in terms of how much code do you have. One thing that you don't have is that you cannot like take the value and increment like to this sort of thing in one line. You would first need to copy and then explicitly increment or multiply or whatever you want to do. And the last type of operators we will take a look on today are bitwise logical operators. So while these operators here that we had at the beginning work on a on the level of entire expressions and can influence your control flow, the bitwise operators are well, they are mathematical in nature. They are not programming operators like that they change things in your control flow, or that you can use directly to specify some condition, but you just use those bitwise operators to mathematically manipulate your variables. Of course, you can then use them like you can use the plus and other things in your later conditions. So it's not like they're not useful there. But let's go quickly through them. So let's use a char for this. Test 1 null x. So let's 1 2, that one will have 0 1, oops, 1 1, and 3, which will have a 0 here. So we have some of our bits, oops, that's wrong, some of our bits set, and now we can char test here use a logical operator. So we can, for example, use the OR operator, bitwise OR. So if we this or or that, the result is just this and the other one set here. So it just works like the normal OR operator that you might know from I don't know, I guess you had logic at school. 5. The next example, let's say 5 here, and let's go for 2 and 3. 2 and 3. So like with the OR, all the bits are set which are set in any of the variables. With the AND operator, you only end up with the bits set which are set in both of them. So that was 3. So we had set 0, 0, 1, 0, 0. So this bit is set in both, so it's set here, but here only 1 is set, so it's not set. And then we can also have a XOR operator, which is an exclusive OR. It's on the same. And the XOR is like if they are the same, they will be 0. If they are 0, there will be 0, but if only one of them is set, then they will be 1. So in the XOR case, 2 XOR 3 gives us this result. And finally, we have just negation. 7 ist gleich tilde. Which one we want to negate? Let's negate this one. So here it's equals okay, so what was it? Number 2 is so wait, that's not right, that should be B here. Sorry about that. 22, so null. Damn it. Null B, so it's negation of this, so 1 1 1 1 1 0 1 0. Wait. I think that's already it. Yep. So that's the negation. It just inverts all the bits, takes ones, turns ones into zeros and zeros into ones. And then the last two operations are bit shift operations. They are also quite nice. They move the whole bit pattern to the left or to the right by a specified amount of places. So char test test 8 is equals, let's go with our test 2 again, and let's shift it to the right by 2 places. So the result will be 0, B, 1, 2, 3, 4, 5, 6, 7, and 1. So we basically took this thing here and we shifted it by 2 places. So we take this part and prepend 2 zeros on the other side, and then we get this. And then we can do the same thing into the other direction. Char 9 test 9 is equals test 2 left shift 2, and then the result will be we take our thingy, we remove 2 zeros at the beginning, and we then put 2 zeros at, I drop the B, 2 zeros at the end. So it shifts in the other direction. And a very useful thing to notice when doing this is that shifting a number in binary representation by one place into towards the right is equivalent to a division by 2, and shifting it to the left is equivalent to a multiplication by 2. So in certain scenarios, if you only need to multiply and divide by 2, you can just use these bitwise operators to increase the performance of your code, since those operators are very quick to execute, while a actual full multiplication or full division, at least on less optimized CPUs, will take many CPU cycles. So on modern Intel CPUs, I think they can do it in one clock, but many microcontrollers like Arduinos and alike, or old Intel CPUs, they will need many clock cycles. And another thing to note here is that multiplication is much faster than division, which I guess is intuitively understandable. And there is one more thing that should be taken into account when using these bit shift operators. So if we are shifting to the left, it always shifts in zeros, but if we are shifting to the right, whether it shifts in zeros or ones will depend whether the number is signed or unsigned. So we can make a test here. Int test s for signed is equals null x ff. Actually, we could go with char as well. Just fill the char with ones. This is equivalent to is equals minus one. Minus one. And this is actually something you can use when programming. And if you want to fill an unsigned integer of a unknown size with all ones, you just assign -1 to it. This will always result in all f's, no matter how large it is. So if, for example, if you have a size t or a int ptr type, which you, depending on the platform, will have a different bitness, you can just assign -1 to it if you want all the bits to be set to 1. You could also assign the inverse of 0, that would also work, but -1 is kind of customary to do so. Okay, anyhow, if we now shift this, and we can in fact combine even those operations with this. So let's go and let's say let's give us something that we can put a breakpoint on. So this line is just so that we can put a breakpoint on something. It's complaining. We already had test 2, test 1. That should be var2 in this example. It also complains if you are trying to using uninitialized memory. So if you go to locals and then to var5, no, sorry, that's not the breakpoint we wanted, to test s. Test s, you see here, okay, we need to enter hex display, that it still is all f's despite the fact that it was shifted to the right. And if we would make this unsigned, should do this by just making another test case, test u for unsigned. We will notice that when we do the shifting with the unsigned version, it will shift, you see it's 7 because it's shifted a 0 in. And another thing to keep in mind is that if we would do this with something that is not a negative number, so I think f77 should be the highest positive one we can have, and we shift this to the right, then so it checks whether the highest bit is set. If it's a signed number and you shift to the right, it checks whether the highest bit is set, and then it shifts in this bit that is set. So here you see, since we started with test s2 being f7, so 0 1 1 1 1, it checked that the highest order bit is a 0, and then it shifted in a 0, not a 1 in. So maybe I should write this as a comment. This is something that is good to remember because it's a nice source of errors. So it's easy to screw something up this way. Okay, this examples we already had. Okay. So there we have our registers. That's also useful. And one more thing that is good to know about variables and data types is that if you don't want to use numbers, because numbers are non-described, like you have flag 355. What does it mean? It's for a human it's unintelligible garbage basically. So to solve such sort of issues, there is a thing called enums, and an enum allows you to assign names to numbers, like my enum 0 is equals 0, and my enum 1 is equals 1, and so on and so forth. And you don't need to specify like any number. So if you make 1 or any number, it will continue just as you see with the intelligence here. It tells you, it just adds 1 each time. Here you have 10, the next one will be 11 automatically, then you set 22 and 33 by hand if you want to keep a value range. So it's quite nice. And here you can specify which type your enum should really be. So if you now write enum, we wanted to this in scope, var1 is equals var1 is equals enum1. From the computer's point of view, this thing is completely and utterly equivalent to writing char is equals 1. The names you have here do not survive the compilation step. They exist in the source code, and the compiler knows which values to take, but once it generates the machine code, the enum is just a normal machine type with a certain value assigned to it. And you can of course use those enums in conditions. So where's the mouse? When you scroll up, when we were here, it's more okay, let's say, okay, let's copy this example. Just use my enum instead for the first two. Assign my enum 2 and my enum 2. Yeah, exactly. You can get rid of this and then compare this with my enum 2. One thing that is important is that of course if you have those types, then it will not want to take a number, and it will also not want to allow you to this should not allow you. Okay, here you can make plus, this is fine, but the result will be an integer, not an enum, so the assignment then fails. You cannot use numbers here. You could of course use typecasting, which is the next thing we will take a look on, to force that. But the general idea of enums is that you can just use them as placeholders for whatever value that can be held in a standard type. You can then have a nice readable name that will be very helpful to you. And another thing you can do is you can have this mechanism without enums. You can use this preprocessor, which we took a look on in the last lecture. Define my one, and then you can let's combine these examples together. So, and yes, you can compare enums to a number, to an integer number. This will be fine. This will the compiler will not complain then. So this was supposed to be my and not mm. But generally, the thing is that enums are more recommended to use because they also enforce that you cannot assign an uncompatible value. So if you would have values that denote a certain property and then another set of values would denote another property, and then you have a function which takes 2 arguments, then if you would just have 2 integers as arguments in the function, then you could like have the wrong order of the arguments or some other mistake. And if you are using enums, then you are guaranteed to use the right types and right values which you can use. Okay, so this much to that. And one more thing that is quite helpful, you can use the typedef keyword to rename some types. So So for example, in 64, or let's go with in 64, you can rename this to int64 underscore t. If you want, wait, why is this complaining? Type def. I guess this one already exists somewhere in the definition. Yeah, I had a typo. T. And then you can use this as a type. You could do more or less the same thing with this define, just in a different order. So hash define t like this, but type def is recommended to be used. It also gives more information to the compiler with regard how to help you with IntelliSense and stuff like that when you create types. The next advantage of using these types is that it prevents you, like with the enums, from assigning incompatible types, while this typedef method would not. So it would be more prone to errors and programming mistakes. So the next thing, as I already mentioned, conversion of data types. So if we have a value of some particular type, let's say we have an integer, so int typecasting. So let's have int var1 is equals 1, and then we have another type, let's say a short to var2. We can in fact assign var1 to var2, although it will yield in a loss of data, and depending on our warning setting it will also generate a warning. So it will just copy only the lower portion of the, so let's say if we would assign this null x 1, 2, 3, 4, 5, 6, 7, 8, to var2 will result in just being the lower portion of var1, and the compiler will in this case generate a warning because it will not want you to do such things, to lose data. Of course there are use cases where you might really want that on purpose, so in which case you would write it like this, so that you say convert this type, and you kind of are saying the compiler that you know what you are doing. And what you can also do is you can also use this to assign a integer to a floating point number, or vice versa. This assignment will be will not lose data in this case because it's a small enough number that can be fully represented by the double. But if you would be assigning a 64-bit number, so a int64, it would in fact throw you at least a warning that you might lose some data while doing this assignment. And of course if you assign the other way around, so if you have double var4 is like 1, 2, 3, 4, and then you want to assign it to int var5 is equals var4, then var4 will result just in having 1, 2, 3. The comma will be stripped, and we can put a breakpoint here and take a look how the compiler will. Oops, did we reuse a variable? Yes, we reuse the variable. Okay, let's just get rid of that. So as you see here, you have a specialized move. Sorry, we are not where we wanted to be. We don't need this breakpoint here. We have specialized move SD instructions, which are this one, which I even cannot pronounce, which can be used with floating point numbers. And you also see that here we are using different registers. So in this case we use the XMM0 register, and this is they are unfortunately not shown here in this register view. Maybe we can enable, yeah, we can enable them by adding them. And as you see, you have also SSC or AVX. So as I mentioned earlier, there are quite a few of these vector extensions, and they are used for also for floating point operations. So this MMX registers, for example, are used by default. MM and MMX registers are used by default for floating point numbers, and you will not be normally storing floating points in this normal integer registers like RX or R9 or R12. You will always use some of this floating point registers to store these values, and then you have, of course, completely different opcodes to make operations with floating point numbers. So in this case, here we need two operations to load the value into our register. One operation just assigns the value to a register, and the second one writes it from the register to the memory. So the move SD operation is like our move operations, just that instead of the R something registers, it takes the XMM registers. And then if we want to cast a number from integer, from a double to an integer, we use this cast VTTSD to SI, and there is the opposite opcode here, which does the opposite, cast VTSI to SD. So this much to this. And what else could be interesting? Yeah, what you could do in principle when casting things around, you could in fact force cast a integer or a double to an integer in a way that would bypass the proper casting method. So let's quickly do that. Int 64 6 is equals. So this is of course not what would be normally recommended to do, but it's something that you can do. You can take the memory address of our var4. So this AND operator that will be explained in the later lecture in more detail when we look on pointers and references and variable operations, stuff like that. It gives you the memory address where variable 4 lives. It's the reference operator, and then we can tell using the cast operations that at this memory address we don't have an integer or a 64-bit integer living, or rather a double living, but we have a 64-bit integer living. So we have an address to a double, which we, through the use of the casting operator, turn into an address to an integer, and then we can use the asterisk operator like this to read at this memory address using the type provided. So what we will do here now is we will just need something for the breakpoint. We will copy the binary representation of 1, 2, 3, 4 to our integer register. So when we look on this in the disassembly, we will see that we are again here using our regular operations. We have rex, we have move, we have rex. We are operating as if our variable 4 would have been a integer value, despite the fact that it is not. And now if we look into our integer value, we see that there is a very strange number inside, and this is pretty much the binary representation of this floating point number. And what we can do, there is somewhere a list that explains all the formats. So here we have a link which you can later review. It shows you pretty much the exact representation. So you can enter a number 1, 2, 3, 4, and then it will tell you the representation here. Wait, what it was? Okay, this is just floating point. This is not this is a float, not a double. So it's only 32-bit, and that's why the representation here is slightly different. We can change our example to use float here, and then we just go to int. Okay, and we forgot our So the thing is, you cannot really set a breakpoint on something that doesn't do anything, so you need always at least some sort of dummy operation if you want to have a breakpoint somewhere. And here we see it's 4 to F6 CCCD, and that should be, yeah, 4 to F6 CCCD. So we see that we really managed to retrieve the right type, the right content from the memory address. So you might wonder when would you need to retrieve the binary representation of a floating point number. For example, if you want to write something to a file or some information to a file and you don't want to have a textual representation, you need to write the binary representation of your floating point number then to save on your Dingsbumster, to save it to the file properly. So this much to typecasting and type conversion. Now this type conversion, like demonstrated here or like done here, let's make it explicit, you can use with many types, and as it becomes somewhat intuitive with this behavior here, you can cast types to each other which are completely incompatible. So you could also use typecasting to cast. So if we have here our enum, for example, it does not have a value 444. So let's define an enum. Var 7 is equals my enum 0, and then we want to assign our enum the value 44. So we can just typecast 44 to our enum, and then if we put a breakpoint here, we don't need that. Okay, 0 of course doesn't work. We need to have our dummy line to be valid. But using this typecast, we still were able to assign well, it's hexadecimal, so let's have hex. To assign 44, which is not one of the valid values for this enum. And you can of course use this also to assign, for example, the float. We could do this as well. We want to break here. So now it will assign the value 1 to 3, because it will treat it like an integer. So as you see, this typecasting is very powerful, but also very dangerous, because you really can typecast anything to anything. And the dangerous part is if you are just making a typecast like here, where you're just assigning one type to another. If the assignment is okay, then within reasonable, then it will either assign without a warning at all, or it will assign just with a warning. But if you do an explicit typecast like this, you can assign anything to anything and pretty much break things very badly. So this much to this. We have not went through everything. One more thing maybe that we can take a look with regard to this binary operations here, to demonstrate another use case for those. Could be flags. So for example, if we have so what you can, for example, do is you can define some individual bits to be flags. So like here, every single bit is a flag, and then you can, to one variable char f-test equals assign multiple flags, like for example the first flag or the next flag. And if you want, let's add the fourth flag. And if you want to add even more flags, then you could do it with this OR operator. And then if you want to add one more flag, so if you want to add one more flag, so set a flag, you would just use the OR operator in combination with the assignment. So as we already see, we can this way assign in one line something, and what we also can do is we can clear flags in a comparable way. But here in this case we use the AND operator, and then we use the inverse of the flag that we want to get rid of. So the first flag makes just an OR, so it adds another 1 to our value, and this one here makes everything in this flag 1 except what it actually was initially, so it will clear only this one flag. So clear. This is used often in programming if you want to save memory. You don't want to have like 100 variables which are all taking 1 byte, but instead you just use a flag variable like this, and you can also set multiple flags or clear multiple flags. But since I'm already 1 minute 2 minutes over time, I will just paste the example here, and that's that. And we need some homework. So I would say that there are 2 things that are a good homework for today's lecture, which are not too difficult. Namely, as I showed you on this website before here, this binary representation, you can write such a tool using set and clear flags yourself. So let's try that. So homework 1. So as an input you will get a float variable, and as demonstrated here you can turn this into an integer, and then you should in your operation have these 3 variables generated, or rather filled, which will contain the values which you see here. So as you see, all these values are just different portions of the number, so you just need to take different portions of your variable, of your initial converted variable, and then assign it to those things. And the operations you can use to do it are bit shifts. So for example, you can shift, so if you want to have this value, you just shift everything by 31 places to the right, and then the only thing left will be this one thing. Here, or if you want this, you will need to shift this by 7 places, and then you need to mask off this place. So you can use an AND operation with just the lowest 6 bits set to 1, then all the other higher bits will be erased. Or if you want, for example, the mantissa, you can also use a masking operation. You just assign and then make AND a number where all the lower bits are 1, and that's it. So I think this is an easy enough homework. And as a bonus homework, you could do the same just for a double instead of a float number. Yeah. I think this is a good first exercise, so we will stop at this point. I'm 4 minutes over time. I'm sorry about that. We'll try to be in time the next time. I will upload the whole project and the homework to the Moodle, so that you can so that you have the examples how to mask things. Do you have an example for masking? Well, yeah, a very simple one here, for example. And the bit shifts and everything, so that you are set to do the homework. Are there any questions? No questions?
I just want to ask, so if this is the homework, then this we have, okay, then we will have like just the lectures, and at the end of each lecture we get a homework and we have an exercise, or how is it?
Well, the homework is the exercise. So you need to make the homework, and that's the exercise you are exercising. I explained that during the first lecture. That, for the most part of the time will be used to explain how C++ work and how those things work on a low level, and you will get homework assignments to complete and to turn in, not on the next but always on the over next lecture. So turn in, like you have to upload them to the Moodle. We will not go through every single submission one by one. If there is the request, I will show a reference solution. But if there are no requests for reference solution, we'll just proceed with new material.
Yeah. Okay. Thank you.
Any more questions? Okay, if there are no more questions, then we will see each other next week. I will upload the lecture and the source code and the homework to the Moodle so that you have everything that you need to successfully make your homework. If you have any questions about the homework during the like something doesn't work out for you as it should, then you can ask that question during the next lecture. So there always is time to asking things. And we will see each other next time. Bye bye.